that's what I want to achieve, and that's a little research project we did together with Chris Seaton from Oracle Labs. He contributed a little bit the experiments in JRuby, and with Stefan Lucas in Lille and at Armored. So what do I mean by metaprogramming? Well, as a Smalltalk group here, you probably know that kind of stuff. I'm sorry, I still used my old slide that's adapted for the more general audience. So everything you see here, you can imagine just with Smalltalk syntax. Yeah. So that's just a little Smalltalk hiding between curly brackets. So yeah, you know, you have your perform in Smalltalk with a symbol. You have your instance reading and instance field writing methods. So that kind of metaprogramming. Here for people from the Ruby kind of a world, you have the same sim as does not understand. You implement a little proxy and then you use does not understand and perhaps forward the call by using perform. Or that's not so much in Smalltalk, having a proper meta object protocol. So that's more like the CLOS kind of Lisp style of things, and that's what I'm actually really interested in. So it's really cool to make that stuff fast, but actually I want to get here. That's research I did during my studies here in Brussels, and the goal is to have something where I can modify the whole behavior of the language just by defining a specific somewhat called meta class. So in my case I was focusing on concurrency. What I wanted is I wanted to have some meta object like a domain that I can redefine so that I, for instance, can provide the semantics of an actor model within my language. So I don't have to adapt the virtual machine to provide guarantees, but I can really just define my concurrency model on top. So either actors or STM or whatever you can imagine. So what I wanted to be able to do is redefine the semantics of writing to fields by just providing such a little snippet. And what you see here is actually almost sufficient to implement a little actor system. So because most important for actors is that you have proper isolation between the actors, so that not one actor can see what the other actor is doing and not access an object graph within another actor. So essentially in a naive version you just do a test whether you're in the current actor or in another actor. If you're in the current one you can just access the object fields, otherwise you throw an error. Now you can imagine that stuff is executed for every single field right in the system. So it's really goddamn slow if you have no way of optimizing that. So yeah, that's a problem. And in general, of course, everybody knows metaprogramming is slow. Why do people know that? Because, for instance, of Java. So, but it's not all that much better if you're working with Coq, because Coq at the moment also is not optimizing it. The idea is you have a method invocation, and when we measure that we see roughly 7x overhead. It's about the same order of magnitude also in Faro or Streak. Same thing with dynamic proxies, at least on the JVM you also see about 7x overhead. So it's much slower as it should be.
And the assumption is that the only acceptable overhead is 0?
The assumption is if you want to encourage people to use metaprogramming and not to avoid it in performance critical code, yeah, then you want 0 overhead. So otherwise you have the situation now that people find workarounds, which perhaps makes the code less readable because, well, in Smalltalk we know a standard thing is you use does not understand, and if you hit it the first time then you generate a method, for instance to delegate to another object. So you avoid the cost of doing the does not understand and the reflective invocation. But then of course you have that strange does not understand handler and all those methods popping up, and who has to maintain the system then doesn't really know what's going on. So yeah, 0 overhead was
changing the VM is out of the question. Changing method.
Well, the idea is to make the VM smarter so that all the metaprogramming facilities are fast. So yeah, the idea is to work at the VM level.
Oh.
Okay. So generic metaprogramming is pretty slow on Java. Compared to that, for instance, on PyPy they have a metatracing just-in-time compiler. That's actually pretty fast. But if you start to implement such a simple meta-object protocol as I showed, then you still get like a 50% overhead. because the compiler, even so it can optimize all those little things, still doesn't have enough information to optimize the example I showed you with the actor meta-object protocol. So we need something better. And what we found here is a nice way of implementing interpreters, and there we also experimented with those meta-object protocols. So I will just briefly show you the way how we implemented interpreters, because I think that's a very nice idea. It's not actually mine. I forgot to put the reference here, but I will put it in the slides I will put online. Okay, before I start explaining exactly, if you see Java-like code, that's application level code. If you see Pythonic code, that's the interpreter level implementation. Yeah, just to make things clear up front. So if you imagine you want to implement a little interpreter, you will probably first start with a parser. For instance, for such a code snippet, you have a conditional statement with a condition expression, then the two branches, then and else, and that will be parsed to a tree like that perhaps. So again, the condition statement and the other two sub-expressions. Our interpreter in the essence looks like that. We parse a file, we get back that kind of a root node here, and then we call an execute method and pass it perhaps a frame which captures all the local variables in the method application. So now the question is, how do we actually need to implement those execute methods for each of those nodes? And that's pretty straightforward. The simplest possible way is really just directly implement the semantics of your language you want. So for instance, you have literals, so the 0 and the 1 here, and the parser will just, while parsing, create such an object, put a constant value in there, and during execution you will just return that. For reading of variables, very similar. There we use our frame object I mentioned before, and we can assume that typically languages like Smalltalk can be compiled in a way that you can just enumerate your local variables, and then you can just map it to an index and access a specific index for each variable in that frame, which has an array to store the local variables. If you write, on the other hand, a variable, that's very similar, but the difference is that you of course first have a sub-expression to evaluate. So here we have our assignment statement, and first we want of course to get the value here. So what we do is go into that child node, execute that node, and get back a value, which we then can store into that frame object at the given index of that variable. Okay. So that's pretty much generic way of implementing an AST, an abstract syntax tree based interpreter, not very fancy. But the main idea is here to actually start optimizing that AST interpreter during execution. So one of the things that's important to really get performance is to realize in Smalltalk, we actually don't know exactly during compilation what that is. So we have here that count statement to increment that count. If you just look at the code, we will intuitively know, okay, there will be just integers. But the important thing in Smalltalk is, of course, also the integers are objects. So one trick they use in the virtual machines is to use things like small integers, where you essentially steal a bit and then represent the integer value directly and don't have to allocate objects. But yeah, so depending on what kind of integer it is, maybe you need to allocate an object. And we want to avoid it. So for the self-modifying, self-optimizing interpreters, we try to actually optimize each of those nodes, for instance, that they can handle integers directly. So what that means in that interpreter, we just compile that little code snippet actually to an uninitialized version of that node. And that node, when it executes, will still execute a sub-expression first, gets a value, and then call a specialized method with that value. And in that specialized method, we as a language implementer can decide on the heuristics we want to use to optimize our little interpreter. And in that case, I decided, okay, I want to use a type, and then actually provide a specific type for the instance variable, right? For the type integer. And yeah, at the moment you see it's red here, and if we execute that, then we will really exchange that node in the tree, and the next time we execute it, we will actually use the optimized node for the integers. So, and that implementation looks like that. So instead of just calling a generic execute method, we actually ask the whole subtree to provide us with an integer, and then we get that returned. Well, sometimes in some code passes that might not be true that it's an integer, then we might need to handle that exceptional case and rechange our tree. But for surprisingly many code snippets, it will work directly, and then we can just optimize it to the integers. And in that case, yeah, if it's a Java-like language you implement your interpreter in, you can properly type all those things to use directly pure integers and completely optimize that kind of AST tree to really use the integers without having to wrap them, without having to tag them, and also the plus essentially can use the direct plus operator of the processor instead of having to do all kind of management instructions around. So for our write node here specifically, that means we can also store the pure integer value directly in our frame. So we have actually a specific second array instead of just having an object array where we can directly store integers to avoid boxing and tagging and other tricks virtual machines usually need to apply. So that's the basic simple idea of building self-modifying, self-optimizing interpreters. And now I want to show you how we actually use that to optimize also reflection. So yeah. That's that part. Here just to give you a little overview what the language looks like. Well, it's still a Smalltalk here, just with brace notation to not confuse the non-Smalltalkers. But as you can see, that's our perform, that's our instance var add put. Does not understand. Yeah, and here's a global, get global, and so on. Let's focus just on the perform. So standard reflective method invocation, you give it a symbol and you have an array for all the arguments. So now the question is, how can we possibly optimize that? Well, let's first look at what people came up with standard message sends in Smalltalk. So that's a classic polymorphic inline cache paper. The idea is you have some variable with whatever kind of value you can imagine in here, and then a plus message send with a one argument. So in the more Java-ish notation, we see directly that message send operator here. And the problem is that one is highly polymorphic. So if we would use a static compiler, we would have to guess what's going to happen there, because usually we don't know. And the idea they came up with polymorphic inline caches is that we actually try to observe at runtime at what happens and then cache the lookup for the operator or for the plus message send, for instance. So, and in those little interpreters, it's called a dispatch chain, which essentially is part of that plus invocation node and will cache the lookup result. So let's walk through how that works. We have our little plus here. We have our count, which has an integer object in it, so the 0, and that dispatch chain starts out in an uninitialized case. And the idea now is that we execute that first message sent here, and then we note, okay, we actually got an integer as a receiver. We do the lookup, we get that integer plus operation, we cache it, and we also have like that check whether the receiver is still an integer, because maybe for some reason the count overflows to a large integer or something, and the receiver changes, so we need also to handle that case. So that's the general idea, and when you now apply a compiler to it, that compiler can speculate, okay, I actually see that's like what we call a monomorphic send, so there's actually only one kind of receiver always been observed, and then it can completely inline that plus operator and do directly the plus operation in your method. So the benefit here is even in the interpreter, it avoids the extra lookup, and it enables inlining and further optimizations by just-in-time compilers. So that's a basic idea. Now back to our little reflective example. So remember, perform with a symbol, and here we actually just generalize that idea. So we have our little invoke node here, and also at the dispatch chain. And here we resolve that plus first. So we note that we get here a plus symbol provided as a parameter, and then we cache that. We have that again, that check in case some other symbol is coming along dynamically at some point. And then we will just nest that kind of dispatch chain again, where we do the thing I just showed on the slide before. So here we will have again an integer node, and then we can cache and inline the plus operator. So, and that provides actually enough information to the just-in-time compilers and optimizers, and allows us to remove completely the overhead of reflective method invocation or reflective field accesses. So all the 7x are gone if the just-in-time compiler sees it's monomorphic all the way through. Okay, so that solves those two categories. So the simple reflective access, and also solves like in combination that does not understand and the message missing, the perform here. So now the question is, what do we do with what I actually was interested in, the kind of fancy meta-object protocols. So remember, we have that kind of meta-object protocol that's really cross-cutting applied to the whole application. So we want to change every single field right. So if we have a little example that's using that kind of actor meta-object protocol, and we have that field right node, well, there are at least two parts where it definitely will apply to. Method invocation is also part I just left out, but definitely all the field right accesses, for them it's not statically known what the semantics is. So we cannot just emit the byte code for writing the field here or something like that, or the native code. No, we first have to resolve what happens on the meta object level. So, and the solution here is applying those caching and dispatch chain tricks again. So the first thing is we observe what kind of meta object actually comes along, and in our case we see, it's actually always an actor, and then we can actually just inline that right to field, and by that we provide enough knowledge to the compilers to optimize it. Interestingly, it's a very generic abstraction, so we can, in case we only have a standard semantics of our language, we did not actually use all that fancy stuff to do something, we can really just directly do the write. So in the end, there's supposed to be no overhead in the system if you don't use the fancy meta-object protocol stuff. Okay, so now briefly to check whether it's actually fast. What I used for that, it's not the Smalltalk you probably know, it's not a Squeak, it's not a Faro, it's something way simpler, because it's much easier for me to experiment with stuff. It's called a Simple Object Machine. It's a little Smalltalk, not exactly in the Smalltalk 80 tradition, much simpler, has been used in a couple of universities in the past. It's designed for teaching, so it's, the concepts are more clearly expressed. Performance was usually not a goal until I picked it up and got it like almost on Java level fast. There are a couple of implementations in C, C++, Java, JavaScript, R, Python, and also of course in Smalltalk. So for the setup here, I used two implementations that are based, one on RPython. RPython is something you might know from PyPy. PyPy is based on that. PyPy is a very fast Python implementation, roughly 7 times faster than CPython, I think. The compilation there uses meta tracing. I'm not going to detail that. The interesting part is just the second one uses a completely different technique that's based on Java. I just wanted to show that actually the technique is general enough to be applicable to all kinds of VMs and all kinds of compilation technologies. If you're interested, you find those two little Smalltalks on GitHub. And so to show you the numbers, that's a little benchmark to show, or a couple of benchmarks to show that actually we can remove also reflective overhead while having the kind of fancy meta object protocol. So imagine all kind of field writes, all kind of field reads, or message sends have an extra indirection level, an extra intercept where you can redefine all those semantics. And the question was, okay, if I put it into the system, do I actually see overhead in the end? And if, how much? So I tried it on both little Smalltalks, and in the end we see about an overhead of 4 or 9% depending on the compilation technology. And the most important insight here is we don't see the 7x overhead, so there is still a little bit of overhead because we have that extra semantics. So at any single point in the program we could change again what the field write means by associating another meta object to a base level object. So there is some semantics that we still need to support, but other than that there is essentially no overhead to speak of, so at least not the 7x we saw before. So now you might wonder, why are those meta object protocols important? Maybe it's not important for you, maybe it's really just an academic thing I'm interested in. So let's look at something more practice oriented. So that's where Chris Eaton came in with his JRuby implementation. So he applied the same techniques also in that context, kind of independently, and he checked what kind of speed up does he actually get on real applications. And with real applications, he looked into a Ruby image processing library, which is a good example where the Ruby people think, also very much in the dynamic Smalltalk way, okay, let's use perform, let's use does not understand to implement our little Photoshop processing library. And it turns out that it's really everywhere, and it's also for every single pixel operation. If you like merge layers in a multi-layer document, they use it. So we have all those benchmarks here, and we see actually if you apply that kind of technique, you get a 10 to 20x speed up on processing images in JRuby. So that's just to show that's really nice. And I think Elliot Miranda was also thinking about introducing something like that into COG. So I hope at some point we also have that in Faro and Squeak. Okay, well, let's skip the demo. That's not really important. So just to sum up, the idea I wanted to show here is that meta programming doesn't have to be slow. So there's a very simple technique, at least from my perspective, with those dispatch chains, which are essentially just a more generalized form of things that virtual machines already do. We can apply that to reflective method invocation, reflective field access, and so on. We can also apply that to fancy meta object programming and perhaps enable new kind of applications with that. And yeah, that's I think the most important bit for me. So if you have any questions, if you would like to read up more in detail, I have a paper draft for that. It's not yet accepted, but shoot me an email. You can get it. And yeah, questions? Okay, thank you very much.